So it's my pleasure to introduce the second speaker of today, Fabrizio Andreatta from Universita di Milano, who is going to give his first lecture on the Eichler-Shimura morphism for GSP4, the holomorphic case.
Okay, so thanks a lot for the invitation, first of all. Thanks also for the opportunity to speak here. Actually, should thank Adrian that pushed me into this, even if I was a bit reluctant, because as I wrote here, it's really work in progress. So some parts of this project have been checked and written up. Some are expected to work, but you never know until you write down things. And the second thing I'd like to actually to apologize. I don't know you, but I personally am really fed up with the Zoom meetings. I mean, I'm teaching 2 classes, having department meetings, having office hours, having part of my social life on Zoom. So it's really too much. It's kind of nightmare. I hope this talk will not be part of your Zoom nightmares. So apologies also for that in that case. So what I'm going to do today and tomorrow is a generalization of work that we did with Andreatta and with Glenn Stevens that Juan Esteban mentioned yesterday for the GL2 case. In that case, for modular curves, we managed to produce so the main theme, we managed to produce comparison results apologize already in advance for my handwriting. Between p-adic etale sheaves and the Rham sheaves. So with Glenn Stevens, we did sort of coherent sheaves only, but then with the subsequent work with Adrian, we upgraded those results to the Rham coefficients, so having also connections. In that case, in those cases that we treated with Glenn and then with Adrian, we dealt with the modular curve here. For apologies for the different notation from what Vincent and George used so far. Here it's the toroidal compactification of the SIegel modular threefold, which classifies, sorry, I see that I'm on an old Blackboard. I have to change Blackboard, sorry. Apologies about this. So main theme. Comparison. Results. P-adic etale coefficients. The Rham coefficients over, so we said xn. So this is the toroidal, smooth toroidal compactification of the SIegel threefold that classifies principally polarized abelian surfaces up to, well, things at the cusp, which I'm not going to discuss, over with full level n structure. And here, actually, n is an integer. Bigger equal to 3. and P actually will appear later as a prime equal to 3 also, which does not divide n. And actually, at some point, we'll also have some divisor D, which is the boundary divisor of our toroidal compactification. It will play a role as exactly in the sum talk yesterday, when he had to introduce interior cohomology to have good comparison results. Okay. So why the SIegel threefold? Well, that's a first example where we started studying certain phenomena, and we are sure that actually part of what we're going to say will hold for more general Siegel varieties, maybe more general Shimura varieties of which type that we don't know yet. So that's really one kind of generalization of what one could go into if you want to go from more general varieties. There is a second generalization that I should mention that is more in the spirit of what Juan Esteban yesterday mentioned. So what I'm going to talk today and tomorrow is really a generalization of half of the Eichler-Shimura morphism in one direction. There should be other ones that we are not investigating at all, but they should be there, exactly as in the elliptic curve, in the elliptic case, as discussed in the talk by Juan Esteban. Okay. So in our talk, in this and following, so there will be an algebraic group, as in Vincent and George talk, but in our case it will just be GSP4. Okay, and I will also fix V a standard space, and I want actually to give name to the basis elements. So this actually will define the sort of the standard representation of the group G with the property that the symplectic form with respect to this basis, exactly as in George talk, will be all this familiar shape. And there will be also a torus floating around, which will be things of this type. It's not a maximal torus because, sorry, there is the center also of this group G that I'm not going to consider. And if underlying K is a pair of integers K1 and K2, actually I will denote again by underline K the character to GM that associates to such element of T, the character T1 to the K1 times T2 to the K2. Okay, so this is just to fix some notation. And okay, then we have the sort of Siegel parabolic and the Borel, the Levy that already appeared in this talk, the previous talk that I'm not going to introduce again. Okay, so let's start, try to start gentle, and let's try to review the classical case of the comparison morphism. Okay, so we want, as I said, the etale sheaves and the Rham sheaves that we want to compare, and actually the comparison between them, once we take cohomology, will give also the classical Fontaine type comparison isomorphism between Galois representations and sort of the Rham, maybe even phi modules with filtrations and so on. So let's see what kind of coefficients we want. So on the etale side, so remember, actually, before introducing this, let me recall that we have an object A over Xn, which is the universal semi-abelian scheme. So the cusp between the generate exactly as the four modular curves, the universal elliptic curve will be generated to a GM. And actually we will use this to this A to construct sort of the standard etale coefficients from which we will build others once we take a specific character underline k. And on the etale side, we take the p-adic Tate module of A over yesterday, actually, Juan Esteban already mentioned that you can sort of cook up a topology which takes into account also the boundary, and to which actually this local system that whose rank jumps, if you consider just the etale topology on the xn, actually the rank will remain constant. So I will have a locally constant rank for ZP module over the full xn, if I consider this topology. And of course, to have that etale thing, I should remove P. And then I also have at the Rham side and in this case, I have the relative cohomology of A relative to xn. This again, there is a way to extend it canonically to the cusp itself. So I consider it as a locally free rank 4 OXN module. And it comes with a Hodge filtration. And it has a connection. And here, well, the fact that things at the cusps might go wrong, I have to add log poles along the boundary divisor in order to have a connection. So this is Gauss-Mani. And from these two, actually, I can hook up, if I fix a dominant weight, so a dominant weight K1, K2 in Z squared with K1 bigger equal to K2 bigger equal to K0, I can hook up other etale coefficients than just the p-adic Tate module, and also the Rham coefficients. And so that was what Vincent yesterday mentioned, that you have, if you have a representation of G, you can get vector bundle with connection and also etale coefficients. And in this case, the representation that is associated to this weight. So remember that we call this K underline. So this is associated to the algebraic representation, which is given by inducing. So you have the Borel subgroup that maps inside the symplectic group that maps to the torus. So you take your character as a representation of the torus, and you induce to the group G. Okay, so it's an algebraic representation of G. And associated to this, as Vincent explained, you can construct coefficients actually on this Siegel variety. How do you do that? Well, we define some torsors. So this is etale and T de Rham are certain torsors on which you have an action actually of the Borel. And if you take functions on these torsors that's transformed nicely under the Borel, and nicely meaning through the character underlying k that I fixed, I get exactly my representation. So the first torsor, it's actually given by the symplectic isomorphism of PPA dual and VPA dual. So this VP is just V tensor GP. Okay. So here, sorry for these duals. I mean, you have a principal polarization, so you could forget about this. But at some point, otherwise, it will get mixed up with how the direction which certain maps go to. So please just ignore this. So you see, you have a torsor. On the left-hand side, you have an action of the fundamental group of the SIegel variety. On the right-hand side, you have an action of GZP that acts through transformations of VP. So VP is simply V tensor GP. I have similarly a Rham object, which are symplectic isomorphism. And here again, I have this funny duals floating around. Sorry about this. And I have such an isomorphism. And here again, I have an action of my algebraic group G over Xn. Okay. But on the other hand, on HA dual, you have a filtration, you have a connection, and so on. So this torsor has two structures, right and left. And then we can consider, given our character chi, I define WK algebraic, because we will make this construction in a little while analytic. And that actually will be the families of coefficients that we will consider. Okay. Star. So star is etale or Rham. So it will be simply the functions on T star that transform under the character chi via the right action of the Borel. And still, you see, in the etale case, you have a left action of the fundamental group, so you have a local system. And again, in the Rham case, you have a connection, you have filtration, and so on. And okay, so locally, for example, in the Rham case, this is an algebraic construction. So a remark one, okay, so this will be the coefficients that actually you can do this also, do this in the Hodge case. It I can consider P Hodge as isomorphism simply of omega A with OX and squared. Okay, so we are missing here the connection and so on. So it's just part of the Hodge filtration. Here you have an action of the Levy, which in our case is GL2. And here you have actually the Borel intersected with M, which is the Borel of GL2 that acts. And you can do a similar construction, and actually one defines the sheaf, the nice coherent sheaf of differentials that actually appear as graded pieces of the Rham coefficients. So this is simply the functions on P Hodge on which the intersected M acts through the character chi. And actually in this case, one can compute it simply sim k1 minus k2. This will play a crucial role tomorrow when I compute a certain BGG complex. Actually, it will be fun. So to remember this, tensor the determinant of omega A k2. So you see it's already these Hodge bundles when K1 and K2, when K1 minus K2 increases, you see that the rank gets bigger and bigger and so on, okay? And this actually, this omega K is the first piece of the Hodge filtration. On this WK to Rham algebra. Okay, this will be important tomorrow because it will give us the highest weight vector on which we will compute certain things. Okay, so that's remark one, just to get to more familiar objects. So you get the sheaves whose sections are modular forms. And there is a remark two that I want to make that will also play a crucial role later on, that in order to define my spaces VK algebraic, it actually suffices to consider not isomorphism, so a simplex, not simply the torsor that classifies a symplectic basis of the p-adic module or the Rham cohomology, but to consider a basis of a Lagrangian subspace of TPA or HAU, okay? So just fixing two elements that can be completed to a basis and that they pair through the symplectic isomorphism to zero, okay? Why is that? Because you see, if you look, so this VK algebraic is defined by letting the Borel of the SIegel, the unipotent of the Borel of the SIegel acting trivially, right? Because the map, the Borel acts through the quotient to the torus, and actually, that in particular, the unipotent of the SIegel parabolic acts trivially, and actually that amounts to say that just fixing the first two elements, if you want, of your symplectic basis is enough, because that's exactly the sort of the degree of freedom that you have in completing this basis to a full symplectic basis. Okay, and actually this will be important. So here you just have two elements that we are fixing, not four. Okay, so that's remark two. Okay, so now the comparison. So we have seen the perfectoid tower appearing often now, so I will freely use it since we psychologically digested this. So this is the perfectoid tower, which is defined at the toroidal level by trivializing symplectic trivializations. TPA isomorphic to VP. Okay, so that's the full sort of Galois cover of XN through GZP. So it's a profinite Kummer-Etale cover, if you want, that classifies such isomorphism. Okay, and here again I should mention work actually of, as was done yesterday, of Jiao, Lan, Liu, that sort of defined this, extended this profinite cover to the Kummer setting, so allowing inertia at the cusp and so on. So I'm not entering into this. Maybe let me just mention the names that I've written down somewhere. No, well, when I somewhere well, okay, never mind. So I will need this this theory, okay, and then on the good point is that on this perfectoid tower we have this very big perfect these period sheaves, which in our case will be O be the Rham, that actually gives, we have also an isomorphism between the p-adic module, dual, tensor ZP O be the Rham with HA. Actually, here you see the fact that there is a dual on one side and there isn't on the other side. It gives a bit of a headache. For example, as we saw in the previous talk, the flag variety, if you use this upper SIegel parabolic to define the Rham coefficients and so on the SIegel variety, you should consider the opposite SIegel parabolic to define the flag variety receiving the period map. Okay, so there is some twist here with this dual that gives a bit of headache, but let me ignore this issue. And also you can ignore this dual if you want because of the polarization, okay, the principle of polarization. So you have such an isomorphism, and on cohomology, actually it gives this Eichler-Shimura in weight K, okay, which is exactly the thing that I want to take care of. So if I consider the profinite cumulative topology of Xn over Cp of this coefficients, algebraic etale, and I have the dual here. Actually, there's an extra dual that I have to take into account. Sorry about this. If I tensor this, so this is a QP or a ZP module, so I tensor with ZP with a classical Fontaine ring with Rham. So sorry, I have to write this isomorphism vertically. So that gives an isomorphism with the Rham cohomology of my SIegel variety over QP with this the Rham coefficients. Sorry, I think it was here, right? I hope I didn't mix up the of HA dual. And here again, I tensor with QP with the Rham. Okay, and here you need sort of some vanishing results of the high direct images of this big sheaf of the Rham that actually have been computed and proven. Actually, here is where I've written the name. So, yeah, Len, you. So, to make actually the approach of Scholze of the comparison isomorphism for smooth, proper analytic variety work also in this context where you have things that the divisors go slightly wrong. Okay, so there is they prove the vanishing results that one need to get exactly this isomorphism. On the left hand side, you have a Galois representation. Okay, actually on the top. On the bottom, instead, you have a QP vector space with a filtration. You also have a Frobenius, and the structure, the Excel structures that you have on the Rham. So you don't have a Frobenius, but you have a filtration. You have a Galois action. Actually, make this isomorphism compatible, taking the tensor structure on the two sides. Okay, and there is a remark 3 that I want to make, actually. And the remark 3 is that, in fact, one can prove that the cohomology of this object here, so let me simply write a star here, otherwise I will just spend too much time in rewriting the thing. Actually, this can be computed also on Q bar. Okay, so because those representations of the coming from the p-adic Tate module really relies on the Siegel variety over Q bar, and actually, or you can go to C, in fact, if you want to, if you fix an isomorphism with CP and C. Okay, and actually using the fact that Hermitian spaces are simply connected, this is actually group homology of some arithmetic group. So gamma n is an arithmetic group. For example, of matrices converge to 1 modulo n that defines the full level n structure. Again, of the same kind of coefficients, now viewed as representations of gamma n. Okay, and actually this is important because these objects have been put into families. Okay, and here's actually so the motivating question of long-term projects with Adrian, with Glenn, and Stevens, and with Vincent is actually understanding p-adic variations of this Eichler-Shimura K. Okay, and actually, so things don't fit on one sheet. So I will just reduce for 1 second the dimensions. Okay, so that I will have everything on the screen. Sorry about this. I will enlarge it shortly again. So what does it mean to vary things p-adically, and why? Okay, so let me just mention a few mottos to sort of to advertise why we think this is important and why this attracted our attention. Okay. Okay. First of all, because if you vary p-adically things here on the right hand side, you have p-adic families of monoforms. You have eigenvarieties as constructed by Coleman-Maser in the elliptic curve case, that we constructed in some cases together with Vincent in the Siegel case. Okay, and we would like to sort of complete the picture in the sense that Vincent mentioned yesterday, because this actually left-hand side, we know thanks to work of Ash Stevens and Urbain, maybe David Hansen. So we know what it means to sort of p-adically vary this this object, this left-hand side of the picture, in the sense that there is a theory that sort of takes instead of algebraic induction, locally analytic induction, and then takes the dual of those, and you get space of distributions over the weight space, and you can represent the cohomology of those for our preferred arithmetic group in terms of a perfect complexes on which U operator acts compactly. So there's a slope decomposition, okay? So that induces slope decomposition of the groups and so on, okay? So there is many instances where sort of the left-hand side of the Eichler-Shimura isomorphism has been p-adically interpolated, okay? So that's apropos p-adically interpolating this picture. So this has been, it's well documented, okay? And while the right-hand side, we had some examples in work together with Vincent, but now thanks to work of Boxer and Piloni, Vincent, Boxer, and George, we have even more examples where actually the right-hand side, if you don't work with these Rham coefficients, but it's credit pieces, so in the Hodge setting, you can deform in various ways, and one might want to sort of compare these two possible approaches. And it's not only a curiosity, because, for example, in GSP4, there is ongoing work, for example, of David and Sarah, together with the son and Chris Skinner, and work of Bertolini, Seveso, Benerucci, where etale classes and Euler systems are constructed on the left-hand side, and you would like to have a reciprocity map that connects them to the right-hand side of this picture in order to relate those to special values of p-adic functions and so on and so on. So it's not only a curiosity, the fact that one would like to sort of relate the two sides of the picture, etale and the Rham, for example, to compare simply abstractly eigenvarieties, but good motivations. For example, in the GSP4 setting, why one would really want to have this and use this. Okay, and actually, this was actually also our motivation to first focus on this case. Okay. Okay, so to p-adically interpolate, I will discuss first very briefly how you interpolate these coefficients, these etale coefficients, this 0.1. Then I will explain how actually you interpolate, so to interpolate the right-hand side, we need, as we learned from the two talks by Vincent and George, that actually you cannot work on the full SIegel varieties, but you need to work with the subloci that are defined in terms of the Schubert cells of the flag variety. Okay, so that's the second theme that will appear that I want to discuss. And then on those things, on those loci, I also want to explain how we p-adically interpolate the coefficients. Okay. And we will do actually two examples. So let me bring back things to normal size. So two instances. So there is a case one, which is the holomorphic case. Where things are simpler in the sense that it's a case where the Schubert cell is just one point, infinity, where the coefficients have been studied already to some extent with Vincent. The only thing that we need to upgrade, and actually that's also our contribution, we need to pass from the Hodge case, coherent coefficients, so to speak, to the Rham coefficients. Okay, you see here we have the Rham cohomology, not simply Hodge cohomology. Okay, so but we just need to explain how to upgrade this. Okay, so this is today, and there is a case two, which is the case that actually attracted our attention, where you study the sort of the higher Coleman setting, or the non-holomorphic case. Terminology here is not very good, sorry about this. That will be done tomorrow, actually, where the object on the right-hand side of the Eichler-Shimura has been defined essentially by Vincent in a paper that is going to appear, has appeared already, I don't know, in Duke. And actually, we will see what happens. And in this case, the Schubert cell is just P1. And actually, there is more interesting things happening in some sense, and more and easier in another sense. Okay. Okay. So today I want to discuss case one. And in order to do that, as I told you, on the etale side, so you remember we have three things that I have to explain you how to sort of deform p-adically, or to define where I can define things p-adically. So on the etale side, actually here is work of Stevens or Ruban. You can consider the so you consider the Iwahori group, of GZP. And the coefficients that we consider are just the locally analytic in this talk, for simplicity, we just consider analytic induction from the Borel to the Ivahori of K, and actually its dual, which will be the space that I will denote D etale K, where here K varies in the weight space W for our torus T, which is the adic space associated to the ZP points of our torus. Okay, so here we have so weight can be sort of just analytic, and then we take the analytic induction. It can be so analytic of certain degree n, and then we have also the induction. We'll take that into account. Let me not get into this. Okay, and in this case, what actually Urban Stevens have studied the cohomology of actually the group gamma n intersected with the Ivahori with the coefficients in this d etale k. Okay, in many ways. So they proved that actually you can represent the cohomology with a perfect complex that has an action of the UP operators that are compact, so you can define also finite slope for the Hecke operators on the cohomology. They have defined given control theorems, classicality theorems, and so on, that I don't want to get into here. Okay, so this is sort of well documented in the literature. Okay. Okay. Now I will explain what we do in the geometric picture that will get us to the locus of our Siegel variety geometric side, where we can deform these Rham sheaves. So let me recall again our x and p infinity. Here we have the Siegel variety with the one that Vincent and George were working. So this is the Siegel variety with the Ivahori level structure, okay, that dominates xn. So it classifies principal equalizability surfaces with a full flag of subgroups of the P torsion. Here we have the map pi Hodge state to the flag variety, okay. And this map pi Hodge state, remember, so it's defined by saying, so you have a Hodge state map from the universal p-adic module over x and p infinity that surjects to omega a tensor ox and ox and p infinity. This map is surjective, and the kernel of it defines a Lagrangian subspace. Remember that this actually is isomorphic to VP dual tensor ZP x and p infinity, because we have a universal trivialization of the p-adic module.
Fabrizio, this is not the map pi Hodge state. This is the map that figures in the. That's the map that allows you to define pi Hodge state. Pi Hodge state.
Yeah. So these 2 points. Sorry.
Right.
So,
that map
so it meant defined as follows. Sorry about that. Yes. Sorry. Yes. it's very confusing otherwise. Sure. So the kernel of this map, in fact, I got confused myself. So you have a comparison map that is called alpha Hodge state, and then the kernel of alpha Hodge state inside VP dual tensor ZP or X and P infinity defines a Lagrangian subspace, which exactly gives the map by Hodge state. Okay. Okay, and there is another remark, important remark that I want to make. This is actually due to Piloni and Stroh. That actually you can define a subspace of the invariant differential, which is again locally free OX, and well, you need maybe to take some etale cover of it, so just for etale topology of rank G, and it is an isomorphism if you invert P, such that the map alpha Hodge state comes from an integral map. So alpha Hodge state plus from TP a dual tensor OX and P infinity plus to omega A. So they call it omega A modified. I prefer this capital omega A. I hope it's okay. That actually will help us to define, to follow this map pi Hodge state when we take tubular neighborhoods of Schubert cells in characteristic P. Okay. Okay. So I see that I'm wasting too much time. Sorry about on these things. Okay. Sorry about this. And so we said, so there is a point infinity, and that's the geometric part of the flag variety, okay, which corresponds to the flag generated by E4 dual, E3 dual inside the VP dual. Okay, it's a rational flag defined over ZP, and that defines actually a ZP point of the flag variety. And so we can consider the reduction modulo P. So that defines certain sublocus. Let me just consider CP points to be on the safe side, but sort of you can do things more generally. So this corresponds to flags using these integral structures. So that on V tensor our variety of O flag plus, such that reduce to this one, modulo P. So it is Ivahori invariant subspace of this flag variety, and we take the inverse image as we learned of infinity FP. We take the quotient of the Ivahori.
Fabrizio,
yes.
Can I just ask, when you talk about points in the CP flag variety that have a given reduction mod P?
Yeah. So here I'm using
mod the maximal ideal of OCP, or literally mod P OCP.
Yeah, actually I'm using the evaluative criterion of properness. So the CP points or the OCP points are the same. and then you can consider the reduction modulo P. Yes, sorry about this.
But is it the ideal POCP or the maximal ideal?
It's the ideal P. It's the ideal P.
The ideal P. Okay, thank you.
Yes. So you take the quotient under the Ibahori, and that defines a certain subspace inside the Shimura variety with the Ibahori level structure over CP, and that actually defines a neighborhood that I define to be X Ibahori n less or equal to 1. I don't know if it's a good name, of the ordinary locus of X Ibahori n. So you have a certain component of the ordinary locus of X Ibahori n, where so you remember that on the Ibahori level structure you have a full filtration of by subgroups, and I consider the component of the ordinary locus where actually this is the multiplicative part. Okay, so that's the component of the ordinary locus that I'm considering. And here I'm just considering taking the inverse image of this flag, a tiny overconvergent piece, okay, that sort of you're demanding, if you want, that this multiplicative part extends to a canonical subgroup, okay? And this less or equal to 1 comes from the fact that here I'm considering things modulo P. I could consider things modulo P to the n and take things that reduce to infinity modulo P to the n, and then I would get smaller neighborhoods actually. Okay, so anyway, so there is some neighborhood of this component of the ordinary locus that is defined by this cell. Okay. Okay. So now, 3, what is the geometrical object on the Rham side that we are deforming? Okay, so first of all, so this 3, 1. So I want to first of all briefly explain you what the Hodge part of the picture, because you see over this locus, if you wanted the perfectoid level, so we have a map TP dual. Okay, I have a surjection to omega A if you extend the coefficients. Okay, and I have 2 classes which are A dual and E2 dual and E1 dual, which are sort of canonical classes. Modulo P, well, so you have maybe E dual is canonical, and then E1 dual modulo the span of E dual, which are canonical, that define actually then 2 sections that span ρ2 and ρ1. So these are sections of this integral version of omega A that span omega A because the map is surjective. Okay. And now what one can do is we consider a similar thing that we did in the Hodge case. One can consider the space V0 of omega A ρ1 and ρ2 that classifies a basis of omega A dual, say gamma 1, gamma 2, such that modulo P, so if you take the pairing of this gamma I and this section rho J, okay, modulo P, you get simply the matrix of the form Fp star, 0, star, and Fp star. And here you see some weird duality that interchanges the Borel to its opposite, okay? So you have such, you consider such objects, and this actually should sort of ring the bell with what we did in the algebraic case to define the shifts omega k. And then for every k over our weight space, which is analytic, you can do other things if you work for local analytic characters by going to smaller neighborhoods of this ordinary component that I'm considering. You can define omega k to be the functions on P0, omega A, rho 1, rho 2, that transforms under this character K, that now, remember, it's not the character of an algebraic character, but it's still an analytic character of the Bahari, actually. Okay, so in the algebraic case, we had an algebraic action of the Borel. We took the functions that transform under an algebraic character K under the Borel, and we got a sheaf omega K. You do things in the analytic setting, okay, and we get a sheaf over this X and less or equal to 1, that over which you have those two sections that were floating around. Okay, so here you see we have these sheaves that actually they do not really interpolate the classical omega k that I've defined before, because remember those sheaves have rank that jumps. The rank is essentially given by the difference between K1 minus K2 for algebraic dominant weights. And if you want an interpolation of that, you should have actually a sheaf of infinite rank. Actually, this will be of infinite rank. But if you specialize to an algebraic weight, actually that contains the algebraic sheaves that we defined before. And actually, there is also, we have Hecke correspondences, UP, and what we did with together with Adrian and then Sam was actually to consider H0 of Xn, where you maybe arrange, you take smaller and smaller neighborhoods in order to get compactness of the action of the operator. And we studied actually if we take the cuspidal part of these sheaves, the finite slope part for the action of certain U operators, so you construct eigenvarieties and so on. Okay. Okay, so that's the hot side of the picture, and what's the Rham side of the picture? Okay, so the Rham side of the picture is the fact that with Adrian, we actually exactly as the Hodge filtration is part of something bigger, of a sheaf of rank 2, we managed to extend our sheaf big omega over this region as OX plus sheaves, okay, with good properties, so that the cokernel is also local free of rank 2. Now here we have those two sections row 1 and row 2, actually row 2, which is well defined, and row 1, which is well defined modulo row 2, sections of omega A modulo P, omega A. And then you can play the same game as we did before, and we take sections, this space classifies sections of gamma 1 and gamma 2. Of this H sharp dual. Sorry about this. Such that, again, the pairing with the row i's is in F star 0 star F star. And then we can consider WK in this case, the Rham, as the functions on this formal or p-adic objects on which Ivahori acts. Well, notice that you can actually map down a section of H sharp dual to a section of omega A dual. So there is a natural map that provides actually an inclusion of omega K inside this. Okay. Okay. So my time is over, but let me just mention the result that we can prove is actually construct over this locus X Ivahori, and so at this perfectoid level, less or equal to 1, on this locus where all these sheaves are now defined, we get actually a map from the distribution space of H. Stevens, Urban, and so on, to actually our WK Rham dot, where actually here I forgot to mention, so there is a connection on H sharp, and hence on this WK Rham that gives a complex actually. Omega 1 xn log poles going to WK Rham tensor omega 2 with log poles. Again, on this region, so I'm not adding all decorations. And finally, going to X3 with log poles along the boundary. Okay, and this is actually is WK the Rham dot. And again, here the map is if I add, actually, to get a map, it's already enough to consider certain subsheaf of B the Rham. We'll make a remark of this. That will come into place with the fact that we are just defining half of the Eichler-Shimura maps that we would like to define. And that, upon taking cohomology, and that actually is something that I will come back tomorrow, will give a comparison result. that has actually a Hodge projection that is actually related to the recent work of Diao, Rosso, and Wu that prove a classical Eichler-Shimura map from the space of etale distributions to omega k with some twisted coefficients, but actually not only for just before, but for more general coefficients. Okay, so for the time being, I'll just stop here with this map of sheaves that we get on this pre-image of the easiest Schubert cell. So what I'm going to do tomorrow, just to hope to attract you so that you don't run away from my second talk, I want to discuss the same picture over the other Schubert cell, which is the one-dimensional one, which is a P1. Okay, I will also construct a Rham complex. So we'll sort of refine these 3 points also in that setting: the etale side, the geometric side, the Rham side. Okay, and what I would like to do in the second part of the talk tomorrow is to compute in this case, and in the case that I will introduce tomorrow, the computation of the cohomology. Actually, from the left-hand side, it's the cohomology computed by S. Stevens, Urban, and so on. On the right-hand side, you have a BGG complex, which is not very interesting in this case. Just get generically a complex concentrated in 1 degree. But it will be interesting actually in the other case where you have a complex concentrated in 2 degrees. So you have a sort of a contribution to H0 and to H1, and I hope I will actually show some actual computation of this. And I'll stop here, and sorry for being over time.
Grazie mille, Fabrizio. So, any question from the audience?
So I have a question.
Yes.
This module, well, the sheaf WK de Rham,
yes.
which you mentioned, has a connection.
Yes.
Do you have a version here of the result you proved with Adrian in the GL2 case, that on the kernel of UP you can interpolate powers of the connection?
No, we don't have that actually. No. So we simply have that we know we have a connection, but we don't know that you actually can p-adically interpolate it on say some version of p-depleted modular forms.
Would you expect something like that, or is it just not something you've looked at?
Yeah, I would expect that. I mean, I think there are several things that one need to watch out. So what kind of p-depletion you want, and what kind of iteration of nabla you want, because I mean there are many options, but it's definitely something that I expect. Yes.
Okay, thank you.
I see no raised hand, so maybe I ask you questions.
Yes.
In this theorem, the decay etale goes in the zeros part of the complex, right? WK,
yes.
yeah.
Yes.
And are you going to say something about this being quasi-isomorphic or something?
No. So that's the point. So I just get a map that on cohomology sort of generically. So if you take some open where the weight is analytic, but actually
okay.
Local analytic weight, you have generically you simply have a map from H3 of this etale coefficients to some H3 the Rham of this complex, and actually that will be concentrated only 1 degree, and it actually will contribute to omega k plus the weight k shifted by 3.
Yeah. Okay.
So H0 of that, which is exactly the kind of cohomology when you take
holomorphic
slope. Exactly when you take slope decomposition, it's exactly the case that we consider with Adrian and with Vincent, with one thing, that in our work we had to consider cuspidal cohomology of these spaces, exactly because of the question that came up in the chat in the previous talk, that since you work with toroidal compactifications, those spaces do not live on affinoids. So to have vanishing results, you have to introduce some cuspidality condition on this complex, which actually amounts on the etale side that you don't work with the full cohomology of the arithmetic group, but with the interior cohomology. So the image of the compact supported cohomology inside the cohomology, which is something that sort of rings the bell with what Vincent was mentioning yesterday. So it's yeah.
Okay.
So except for that, yes, there is a comparison then on cohomology group, but it's only a map. And maybe you can say that generally it's subjective, but another part missing, actually many parts missing, and maybe, well, one Esteban in a little while will explain what should be added.
I actually have a question too. Maybe I will turn on the video.
Hi.
So, I understand that those dk et al. And these wk the Rham, they are constructed as kind of locally analytic or analytic Iwahori inductions for the Boreal.
Yes.
So they should be. Yeah, that's a question. So they should be actually. How to say that? I mean, they should be objects which are constructed by pulling back things from the flag variety to the Shimura variety, and those objects there should be like Verma modules or completion of those Verma modules.
Yes.
Right?
Tomorrow, actually, I will give you precisely highest width vectors that span those modules. Yes, in the sense of the Verma modules. Yes.
Okay, so the connection you will define is somehow completely defined over the whole Verma module. I mean, it's I don't know how to say that exactly.
Yes. So that's a bit tricky. That's the computation that we will do tomorrow. So these VK the Rham, they are locally Verma modules. Okay. So this local isomorphisms were not canonical. Only on the grid pieces things become canonical, and that is reflected when you apply the connection. Okay, that is not the connection that you have on the Verma module once you fix an isomorphism given by the infinitesimal action of the Lie algebra of the opposite opposite unipotent of the SIegel parabolic. Okay.
Okay.
Only on the graded pieces, which actually is enough because on that essentially it gives you a description of the Caldera-Spencer map.
Yes.
And using that, actually, you can compute what happens for the Rham cohomology still, even if you cannot describe the full connection.
Okay.
So the motto is, yes, Verma modules are there, the infinitesimal action is there, the BGG complex is there, but it's not an isomorphism with the connection. You cannot do that. You can do it only on the complex numbers, but still, working on graded pieces is enough to put your hands on the computation of the cohomology.
Okay. Okay. See. Thank you.
You're welcome. So tomorrow I hope really to spend the second half of the talk doing computations with Verma modules, in fact.
Okay, and actually, a question maybe you will say then tomorrow. So for the non-holomorphic case, you will achieve a map in the other direction, in the same direction, or how to?
I mean, I cannot. It's a spoiler if I say anything.
Okay, spoiler.
Attract people to my talk. So.
Yeah, that's.
Okay, so I think for today we leave on this cliffhanger about which direction will be the arrow tomorrow. Thanks again, Fabrizio, for your talk.
You're welcome.